Everyone. Thank you, Mike, for the great introduction to the diffusion models. So my name is Bahjat. I'm a PhD student at the Technion, and I'll be presenting a paper of mine called the Denoising Diffusion Restoration Models. So we've seen the great diffusion model as a generative model for image generation. And now we're going to see in this paper how we took this generative model and used it for different tasks. So, as I said, I'm a PhD student at Technion. I've been in the Technion for a long time. And I'm working with my advisor, Professor Miki Elad. I'm one of these people who are like of the new era where my entire PhD is around diffusion models. We research theory and applications. And I was recently at Google Research, where, surprise, surprise, I also work with diffusion models. And about my collaborators on this work, so Miki is my advisor. He's an expert in image parsing, and more specifically image denoising, which was like our in to these denoising diffusion models. And we work with a professor from Stanford called Stefano Ramon, who was at the core of this diffusion revolution that happened in the last few years. He authored a lot of papers on diffusion, but the one I'm interested most in is a paper from 2019, which is actually a predecessor to all what we've seen in Mike's lecture a few months ago. I also worked more closely with his student, or who was a postdoc at the time, on this paper, Jiaming Song, who's currently working at NVIDIA, also with the diffusion team there. And he authored a paper called DDIM, Denoising Diffusion Implicit Models, which accelerated the diffusion process from 1,000 steps to around 20. So that's one of the papers Mike mentioned.
Non-Markovian noise.
Yeah, the non-Markovian model. So this is just to see the impact of these papers. This is the first basically paper in 2019 which sparked this revolution. By Ermon, and this is the paper that accelerated it with the non-Markovian geometric paper. All right. So, what is this task that we're interested in? We're interested in a task that has been studied for tens of years, for decades now. It's linear inverse problems, or image restoration, where we observe, in this case, a vector, but it's an image y, which is our observation. It's our observation of an ideal image. We assume there is an ideal image X that generated this Y. It underwent some sort of degradation operator H, which we assume to be linear, and it has some Gaussian noise as well. So when only observing Y, we would like to recover the X, the actual ideal image that resulted in this Y. So while this is a very mathy setting, it has a lot of very real-world applications. So, for example, super resolution, where we observe a low resolution image, possibly also with some noise. We would like to enlarge it. In painting, where maybe we have a bad connection and some of the pixels arrive, some don't, and we would like to fill in the blanks. Another application is deblurring, where we observe a blurry image. Maybe somebody moved their hand while taking a picture. So that's also fits into this definition of inverse problem. So we would like to restore these images. So just a couple of words of how the deep learning community previously approached these problems. So one way was, well, anybody who took machine learning 101 course was to tell you, okay, so you have your degraded images, you have your clean images, just take a data set and throw it in a neural network, right? Give it to a neural network and ask it to, given Y, predict X, right? You can always take a clean image from some sort of data set, get a low-res version, and ask the model to predict the high-res, and hopefully the model will learn this. But anybody who does this would be right. You can do this, it works, and with certain architectures, it can even perform very well. But the problem is that, okay, so you trained a model for super resolution, it's not going to be able to do deblurring or any other problem. It's not going to be able to do in painting. And in case the noise is very heavy or the problem is very underdefined, we could suffer from a problem where we have a regression to the mean, where our end result would not look like a good image. Another approach, which is the non-supervised training, the unsupervised approach, or maybe some of you may know it as a plug-and-play approach. We say, okay, we have a neural network, we have a model that knows something about the data distribution, about the prior distribution, and we have our own knowledge of the degradation operator at inference time. Using it, we can approximate the likelihood of the current sample X given our input Y. So using these two elements in the base rule, we can recover the posterior distribution, which is the distribution of ideal images given our observation Y. So some approaches sample from this distribution, some approaches give us the peak of it, the maximum posteriori. What we're going to do is that we're going to sample from this distribution using diffusion models. And this approach, what's good about it is that it generalizes well for any task. It can handle any inverse problem, whether it's deep learning or super resolution or painting or any other task that fits this linear inverse problem definition. It might be slower, because we probably need to do some iterative scheme, and it might perform worse than a model that was specifically trained for a specific problem that we're interested in. All right, so okay, I'm going to run through this because I guess you're all experts in diffusion models now. But yeah, so diffusion models beat GANs on image synthesis, the great paper from 2021. Diffusion models are really good at generating images. Okay, what are these diffusion models? So we've seen that we have basically two distributions that we define. One is the assumed model, the Q, which is real, it has no learned parts. It's just a gradual addition of noise over a pristine image. And there's what was called the backward model, or the generative model, which is parameterized by neural network. We do learn something in that distribution. And it's actually the gradual denoising process that we use to generate the images. We have the Markovian assumption, okay. We want to learn, so we do a likelihood objective, as we just saw in Max lecture. We take the evidence lower bound over the negative log likelihood, gets to a KL divergence between two Gaussians, one that is assumed, one that we just model to be Gaussian. And KL divergence between two Gaussians, we know it has a fixed form, closed form. And basically what all this fizzles down to at training time is that given xt, I want to denoise it. I want to basically train a denoiser. Given a noisy image, I want to predict the ideal one that helped make it. All right, and after we train this model, we go to sampling. So in order to do sampling, we start from random Gaussian noise image. I'll just iteratively do, what we iteratively do is that we predict the pristine image. This is what the neural network does. And we add some noise, we add some perturbation to get the next step, and so on and so forth. We do this for a lot of steps in what we call a gradual denoising process, because we started from a very noisy image. And little by little, we remove more and more noise until we converge to an ideal sample. All right. So these were diffusion models in a very quick way. So, and now we want to use them for image restoration in order to solve linear inverse problems. Okay. So again, these are our diffusion models. We have assumed distribution generative model, and what we're interested in doing this time is we want to solve an inverse problem. So as opposed to generation where we just want to generate an image out of nothing, this time we have an observation. We have an observation Y that we want to condition over it. So what we did is that we define a different model. We can define a new Q distribution, a new V distribution that are all just the same as diffusion model, only everything is now conditioned on this observation. This observation is given to us, so we can always use it. Once we define these distributions, we can use them in order to do the same thing. But the problem is that these are conditioned over the input, which inherently, of course, depends on the inverse problem being solved, whether it's super resolution or deblurring. Our definition depends on that. But what we are actually interested in doing, we want to use the same diffusion model, the same model, in order to solve all problems, solve any linear inverse problem. So that's basically what we ended up doing. We want to take a generative diffusion model and utilize it to solve any inverse problem, no matter what the definition of y is or h. Okay. So before I get into how do we actually do that for any problem, I'm going to start with a simpler case. So if you remember, we have our y equals hx plus z. I'm going to start by assuming that h is just the identity matrix, so it doesn't exist, and my problem is simply denoising. Y is a noisy version of x. I want to denoise it. I want to get a sample from the posterior distribution of images given this noisy one. So what we did before that, for generative modeling, in order to generate an image, just started from random noise and continued the diffusion process and generate. This time, I already have a noisy image that is not as noisy as this one. So instead of starting from this part, we're going to start at the time step, at the noise level that matches our observation y, and continue the algorithm from there, where each step still depends on y. So if we zoom in a little bit on this step, the diffusion step, how do we actually do it in sampling? So what we did before that in generative diffusion models, we had the previous step xt. We passed it through a diffusion model, got some sort of prediction, and then we just linearly combined them in order to get the next step, maybe with some random noise perturbation. And that's how we got the next step. This time, in order to do denoising, want to condition this whole process on our observation y. So just throw y into the mix and get the next step. Of course, this is an abstraction behind this green box, behind some. It's still a linear combination, but the actual calibration of the coefficients of each one of the elements needs we need to do it carefully. But for now, that's what we do. Okay. So that was the case of image denoising. What if we have?
If your noise is not Gaussian, it still works?
Oh, so we were talking about Gaussian noise, where we know it's the noise level, know the variance. So there are a few papers on non-Gaussian noise. There's one from Tel Aviv University on gamma noise, and there's one from Technion on Poisson noise. But
it's never really Gaussian noise. We just assume it is.
Right.
The math is impossible if it's not.
Yes.
Right.
If it was, you want all your moments to converge, and in Gauss you get it easily. Otherwise.
Right. So that's why we always assume Gaussian noise, at least in this setting. Alright, so let's consider a slightly more challenging case. Let's say this is my observation. Right. So yeah, I have noise in my pixels that I can observe, but some of the pixels are missing. So in this case, H is the diagonal matrix with some zeros and some ones in them. So there's one wherever I can see the pixel and zero where I can't. In this case, some of my pixels are noisy and available, and some of my pixels are just missing. So what we're going to do, we're going to split our algorithm into two parts. So there's the part where I know something about the image, right? I know the pixel, maybe noisy, but I still know something. And there's the part where I know nothing. In the part where I know nothing about the image, the best I can do is just generate it, right? So I can still start from random Gaussian noise, go ahead and in paint, right? Paint in the missing parts in a similar fashion to what generation usually does. And in the upper part, in the part where I do know the pixels, I want to apply the same denoising algorithm I've seen before. But because I have to keep the steps aligned, I can't do a different process in each part of the image. That wouldn't be good. I have to start from random noise as well in the upper part, in the available part. So we start from random noise. We slowly go towards y, and once we get to a level where we're at the noise level of y, we can apply the denoising algorithm, which tries to reduce the noise that was in Y. So just to sum up, we have three cases here. There's the case where I don't know the pixel. There's the case where I do know it, but the current step is noisier than Y, so my best option is just to go to Y. And then there's the option where I'm behind, I'm already in the final steps, I'm after the noise level of Y, and I want to denoise it. So in that part, if we look at the step, it's the same step we've seen before for denoising. I have Y, I have my XT, I have my random noise, I linearly combine them. The thing is, Y here has a missing part. So because of the missing part, I'm not really going to look at it, right? I'm only going to consider the pixels that are known to me. So we're going to hide that part. And we're going to take it from the other end, from the other case. The case where I don't know anything about the pixels, of course. And then we're just going to do a regular diffusion process without any input from Y. And one might ask, so if these two processes are completely different, how do we make sure that the pixels make sense? How do we make sure that these are not just two completely different images? So luckily, our diffusion model handles that. In each step, we apply a diffusion model, which we can see that in both cases, the diffusion model sees the full picture. It can model the dependencies between different pixels, and in both cases, both here and here, we get a dependency between pixels, so it's still a coherent image. And of course, in this part, we only take the bottom part that is relevant to us, because the upper one we took from the previous case. Okay, so that was the case for in painting and the denoising simultaneously. Let's go to the actual case we're interested in. What if H is just any matrix, any linear operator? So in that case, we're going to remember what we learned in year 1 in linear algebra. We're going to do a singular value decomposition of H.
Michiel-Ad's favorite.
Of course. Yeah. So, I mean, we do learn this in Michiel-Ad's course, so we did have to use it. So singular value decomposition, just as a refreshment, any linear matrix in the world can be decomposed in this way, where both U and V are square, orthogonal, or orthonormal matrices, and sigma is a diagonal matrix, maybe with some empty columns. Sigma has the singular values of our matrix, and U and V are called our singular vectors, their columns and rows. So that's U sigma V transpose. And what's nice is that any matrix in the world can be represented this way. And any matrix in the world, if we consider it in its spectral space, in basically its SVD decomposed space, it's diagonal. What do I mean? Is that if we take a look at the space that is transformed by U and V, the relationship between the input of H and the output of H is diagonal.
Not only diagonal, all your entries are non-negative.
Right. The entries in sigma are non-negative, right? And it's a diagonal relationship. So each point in the input only affects each point in the output, and vice versa.
You can consider it as a kind of a rotation, one in the column space and one in the row space.
Right. So that's U and V, and then there's scaling with the singular values sigma. Exactly. So what we're gonna do is that we're going to take our images X, which H operates on them, and transform them by V transpose. We're going to take our observation Y, which is the output of this H, and transform it by U. And that way the relationship between our observation and our image returns to be diagonal. And in that case, we can still run our denoising and painting algorithm, but only in the spectral space of this matrix. And the nice thing that we prove in this paper, I'm not going to go over the proof, of course, but what we prove is that for any problem, for any H, under some conditions, the optimal solution for training a diffusion model for this specific problem is the same as the optimal solution for training a generative diffusion model. So this theorem allows us to use these pre-trained generative models to solve our inverse problems for any problem, for any given H. So in that sense, we don't have to train anything for our task, for our inverse problem. We can just take pre-trained diffusion model. We didn't train anything in the system, and apply it just with this new sampling process for solving an inverse problem. Any questions so far? Okay. So just to give you an idea of the math, so as I said, we're going to take our x, whether it's xt or regular x, and transform it by v transpose, giving us what we call xt bar, the transformed version of xt. We're going to take our observation 1, transform it by u transpose. And by the way, v and u are both orthonormal matrices, so they don't affect the statistics of the problem. Anything that we can say about the probabilities about xt, we can say about the probabilities of xt bar, and vice versa.
The h is known?
The h is known, but only at sampling time. So you don't want to train a separate model for each h, but at sampling time you do know the h. So you do know if it's super resolution or the blurring. Yeah. And we're going to also scale y by the singular values that we have. And then this very complicated thing goes on, but this is basically our Q distribution that we want to define. I'm not going to go over everything. Of course, we don't really have to delve into all the different symbols here, but important things to notice. We have these 3 cases. These are the same 3 cases we discussed in the denoising and in painting study, where there's a case where the singular value is 0, so that's the same as us not having any information about the pixel. And there are 2 cases where is the current noise larger than or smaller than the noise in the observation, this time scaled by the singular value because we're considering a general setting. And then what we have inside is just a Gaussian distribution that has all these elements we saw in the linear combination. We have our x0, we have our y, and we have the output of the diffusion model, which will come later once we define the learned version of this distribution. So this is the assumed version.
And it's continuous.
What's continuous?
Continuous in the...
Yeah. So the learned version is just, we're going to replace our x0s with the output of the diffusion model. And we're going to want to learn the KL divergence between both this learned version and the assumed version, which this theory under these conditions is basically this simplified version. Our theorem proves that under some conditions, the optimal solution for this KL divergence is the same as the optimal solution for the KL divergence in the generative model. Yeah.
If SI okay, I understand.
So SI is a singular value.
Yeah.
It's going to be non-negative, right?
SI is singular value or sigma?
So SI is our singular value. Sigma is sigma t is the current noise level.
Okay.
Right, and we do have some hyperparameters here, eta and eta b, which of course their choice affects the performance of our model. But the nice thing about DDRM is that we found that we just picked one set of values for the hyperparameters, and they work well across every inverse problem that we tested for. So one more thing, Mike mentioned that diffusion models are insanely slow. Like 4,000 steps is just a lot. So we relied on previous work that accelerated these generative models by skipping some steps, right? And we also skipped some steps, and our formulation allows that. Our formulation also knows how to converge in a very few number of steps. And one more thing, those of you who are more familiar with the singular value decomposition know that it takes a lot of memory. In order to do singular value decomposition for a general matrix, it takes the order of n squared in terms of memory. What we did is that for the more interesting inverse problem, we wrote some algorithms that can do simulate the singular value decomposition in a much less memory consumption. You can do it in an order of n.
What was the intuition behind it?
So the intuition is different for each problem. So let's say for denoising, it's the simplest thing. H is the identity matrix. There's nothing to do, right? The identity matrix, its decomposition is still the identity matrix. For super resolution or deblurring, you can consider it as a convolution, and all convolutions can either be, if it's a separable convolution, you can do the SVD of each dimension, so that reduces your memory consumption. Even if it's not, you can do a Fourier transform, where the Fourier transform, you can use the fast Fourier transform algorithm, and that way you don't really have to store the matrices. For colorizing,
Can you do it in n log n?
right? N log n time, but
Memory. Okay.
this is for the memory consumption. So the problem is that the matrices here are order of n squared, so you don't really want to store them. You want to simulate their operation on a vector. So that way we had a better, more memory efficient algorithm. So basically what I'm showing you in these slides is that we mitigated the drawbacks of diffusion models. We don't have very high compute or memory requirements. So just to sum up what our approach does, we use a pre-trained diffusion model in order to solve any image restoration task, any linear inverse problem. We ended up having a better speed, and as we will see in a few moments, better performance over previous unsupervised approaches. What I mean by unsupervised is that approaches that don't learn for a specific inverse problem, but are general to many different applications. We don't need manual tuning of hyperparameters, just have a single set of hyperparameters that works well for any inverse problem with any image, and also with any data set. And our algorithm can work with both noisy and noiseless observations. So we do allow for Gaussian noise on the measurements, which many previous plug-and-play methods did not account for. You can see here different examples of restorations from DDRM. For example, this is a 4 times super resolution task with some Gaussian noise, an in-painting task, different painting tasks. So either it's random missing pixels, or you want to fill in behind the text in some sort of meme. And there's also deblurring, which also has noise. You have a blurry image, you want to remove the noise and also remove the blurring. These are all reconstructions from our algorithm DDRM. So let's see some more results. Just to see some comparisons. So this is a 4 times super resolution task with some Gaussian noise. You can see the DDRM reconstruction, and the 20 you see here is actually the number of steps. You do this in only 20 diffusion steps. You don't really have to do 1,000 iterations. And what you can see below is that DGP is one of the leading algorithms that are GAN-based that can solve inverse problems. The problem with DGP is that it really doesn't know how to handle noise. And RED, regularization by denoising, it's the previous plug-and-play method that also fails to give reasonable results under noise. Now, for noiseless degradations, RED and DGP perform better. Better than they do here. But what happened? Okay. But not that much better. So even in the noiseless case, DDRM still outperforms all previous methods in unsupervised image restoration. So our measures of success are PSNR, which measures the fidelity to the original image, which DDRM also does better than the rest. And KID, which is similar to FID for those of you that know it, it measures the distribution of outputs. So what this means is that we don't only want to have a great discrepancy, great fidelity to the original image, we also want our images to look realistic. So this is some sort of measure over how realistic the results are. You can see that even though RED in the noiseless case has a good PSNR, the images that we get from there don't really look realistic. And on top of all of that, we also record the number of neural function evaluations, so the number of applications of a neural network in these algorithms. You can see that DRM is at least 5 times faster than any previous algorithm that does this image restoration task in a plug-and-play sense. And for when the measurements are noisy, the delta between our results and previous ones becomes much higher.
Sorry, is it the kernel inception distance?
Yeah, kernel inception distance. Okay, so now we're gonna get to the good part of the presentation where we have some more pictures. So what's nice is that we took a diffusion model trained for the ImageNet dataset, and we can actually restore images that are out of distribution for this dataset. So because ImageNet is general enough, let's say, we can still take images from outside this dataset. These are standard evaluation images in normal image processing settings. And here we have deep learning with noise, and DRM gives reasonable reconstructions. Same goes for super resolution with noise. And this is a nice figure that shows for denoising, when the noise is heavy, we can see the reconstruction of DRM and the reconstruction of a traditional denoiser. It just takes the noisy image and gives us an output clean one. So both do a very good job of removing noise, right? That's the aim of both. But the thing is, a traditional denoiser aims to minimize the mean squared error, like any deep learning neural network. So when we do that, we have a regression to the mean problem. What I mean by that is that, sure, that image has no noise, looks okay, but if you look at the finer details, look at the hair area, maybe the eyebrows, the finer details of the face, you can see that DDRM reconstruction has a much higher level of detail. So if you measure PSNR for denoising, the denoised result is actually better. It has a better overall average fidelity to the original images. But if you look at how realistic the images are, DDRM is much more realistic. And why is that? It's because DDRM samples from the posterior distribution of images given these noisy ones, whereas a traditional machine learning based denoiser aims to minimize some sort of distance. It doesn't care about the quality of the images produced, just tries to minimize some objective. So it might not be a realistic image, but it still gives us a better score. These are more in-painting results that we saw part of. We have the original images, missing pixels in different ways, and DDRM's reconstructions. This is another interesting problem, colorization. We have a grayscale image and we want to restore the color version. So what I want you to notice here is that, sure, this was the original image and this is the grayscale version. But let's look at the teapot. If you only look at the grayscale version, you can't exactly tell what the original color of the teapot was. Maybe you can tell some stuff about it, but you can't really pinpoint the exact original color. And this is a problem even without any noise, right? It's just a grayscale image. So if we just look at the grayscale image, see that there are multiple possible reconstructions. Because DDRM relies on a diffusion process, a stochastic process based on random noise, every time we apply it, we can sample from this posterior distribution, and sampling is inherently stochastic. So we can get multiple different results. You see all these different colors of the teapots, of the bear, of the grass, and all of them are realistic, right? So given a measurement, given some sort of grayscale image or low resolution image, there is not just one ground truth great image that we can go back to. Sure, this image was produced by a single image that we saw in our dataset, but if we don't consider that, if we try to put ourselves in the restoration algorithm's shoes, to say, we only see this grayscale image, and all of these images should be possible. So DDRM can also give us a distribution, a posterior distribution, if we apply it multiple times. So up until now, I talked about linear inverse problems, but not everything in the world is linear. If there was some sort of image that somebody sent to me over WhatsApp, and then I forwarded it to someone over Facebook Messenger, they published it on Instagram, we publish it through all these different social networks. Each sharing platform actually doesn't really send the image as is. It applies some sort of compression, and it's usually JPEG. So JPEG, as you might already know, is a lossy compression format, where we don't actually cover all the details of the image from the compressed version. So when you compress via JPEG very severely, you get these artifacts. So if you look at the bird image, you can see these ringing artifacts and the pixelation artifacts that JPEG incurs. Now, the way JPEG compression works is nonlinear, but still in a paper in Murek's workshop, we also, with the same authors, me, Miki, and Stefano and Jiaming from Stanford, we adapted DDRM to also work on JPEG. For that algorithm, we don't have proofs, but it works. So, like any machine learning, like any good machine learning paper, just works. We can see its results on different quality factors for JPEG. Even for images that look as bad as this dog image, we can still restore a reasonable version without any additional information. And the performance is actually similar to algorithms that train specifically for JPEG, whereas here we just take a pre-trained diffusion model and use it to solve the JPEG problem. And that's one thing I really like about diffusion models, that you can adapt them to all these different applications without a specific training for an application, and they perform well. It's because of all these mathematical formulations that you can play with. It's not like any previous generative model, where you just take the generative model as is. It's a black box that can just generate images, and there's not much else you can do with them. For diffusion models, they're much more versatile.
What did you change here, for example?
So one thing here is that since JPEG is not a linear operation, you don't really have a matrix H. So we can't really talk about even spectral SVD, can't really talk about these things. So what we changed is that we considered like H to be the JPEG decoding, and its inverse to be the JPEG, encoding, and its inverse to be the decoding. And what we did here is some sort of projection to the JPEG space. It's basically if you take the noiseless case for DDRM, it's very similar, but we had to do some assumptions. Because in the linear setting, everything was well-defined, well-behaved, and we could actually prove some stuff. We didn't really change much. It's more or less the same algorithm, but it's not exact. The distributions are not exactly valid distributions because we go through this JPEG step.
So can you consider like basically the spectral equivalence you might consider as this kind of a general Fourier transform?
Yeah, it's a general.
It's general. Right. Can you find something equivalent to the JPEG, or doesn't make any sense?
So because JPEG is not linear,
it's not a Unitarian. I think it's not a isometric, so it might be a little bit problematic. But maybe you could find something.
Maybe. We didn't try to generalize
the linearity is not what stops you.
I mean, the thing about linearity is that it plays well with Gaussian noise. So if you apply linear operator over Gaussian noise, it remains Gaussian. If you apply JPEG quantization or any other nonlinear operation, you lose the Gaussian and you lose the mathematical elegance.
Yeah.
So it's harder to consider. Yes?
Can you talk a little bit about the algorithm? Because you mentioned that the algorithm, you don't need to train the model for each inversion problem.
Mm-hmm.
And then you plug in some math, but you didn't talk about the
so
algorithm.
The algorithm, we talked about the one with the denoising and inpainting, right? So when your problem is inpainting, you...
No. The next one.
The general case.
The general case.
Yeah,
because
okay.
when you showed the math, it was kind of implicit that you're training your model for a v times x for an x bar, which is then dependent on your problem.
Right.
So I wonder.
Okay, so
where's the trick?
So thanks for the question. Let's just look at this algorithm again in this simple case. So in this simple case, the diffusion model still accepts an image and all is well, right? In the inpainting case. Once we go to the more general case with any general matrix, we use the singular value decomposition. And we're going to consider x bar and y bar, where x bar is just v transpose x, and y bar is u transpose y, scaled by the singular values, okay? So once we consider these, all the relationships between them still hold in this way. It's a diagonal relationship. Some of the
now you have a distribution. You don't have a prior of images. You have a prior
Right,
of
right.
of bar images.
So the
which
only
are
problem
not
here-
actual images.
So let's say my diffusion model worked on v transpose x. Okay, in that case, all is well, right? But it doesn't. Of course, it doesn't. Now v, what is v? It's an orthonormal matrix that I know. So just here, 1 second before I put my v transpose x into the diffusion model, just multiply it by v back into the image space. I get an output from the diffusion model, and then I multiply it by v transpose. Because these are orthonormal matrices, transformation is easy, and it doesn't even change the probabilities.
Isometric.
Yeah, it's isometric.
So you plug the v.
Both before and after the diffusion model, you have a v and v transpose.
So in practice, how do you train it? You give it a bunch of tasks.
Oh, we don't. That's the beautiful part.
You
Just take the pre-trained diffusion model.
off the shelf
Yeah.
diffusion model that somebody else did.
Right.
Okay.
So in this specific case of ImageNet, we took the actual model from this diffusion models Bahjat's paper. We just took their pre-trained diffusion model, and we didn't have to fine-tune it on anything, and just apply it to any problem, and it works and shows the results that we've seen in the following slides.
So the part that basically does the indenting is something that you added.
Right. It's the sampling scheme. So the whole paper focuses on the sampling scheme, in the setting where you want to solve an inverse problem and not just generate a new image out of nothing. Right. We'll look at the results again. And yeah, so beyond JPEG compression and beyond the linear inverse problems that we've seen so far, just want to talk a little bit about this paper's impact. So what we did here is maybe in essence simple. We took a pre-trained generative model, the diffusion model, and we adapted it to solve inverse problem, linear inverse problems. We got accepted at an ICLR workshop as an oral presentation and got accepted to the NeurIPS conference. And since then, it has been cited many times, and a lot of follow-up work was based on DDRM. And I'd like to mention a few. So there's this paper that improved diffusion models for inverse problems. They were entirely based on DDRM, and they added some more backpropagation through the diffusion model to further improve the performance. They have some really great results from Yangjin Chang and collaborators. Another similar work from a group in Japan. And there's another paper inspired by DDRM from Tel Aviv University. Some folks in Finland actually took DDRM and applied it to the audio domain. So for diffusion models that can apply audio, they solved audio inverse problems such as audio denoising and even things like removing reverb from a recording. Another very interesting paper that even has denoising diffusion restoration models in the title adapted our algorithm for problems in astronomical physics, which I have no idea about, but it's really interesting to see how DDRM was applied to actual real-world problems from different domains. So this problem in the astronomical images.
But in astrometry, you might reconstruct the wrong images, because just like you said earlier, in the recoloring process, you might get different colors.
Right. So the nice thing is, since you can sample different samples from the distribution, what they show here is that you can get a mean, and you can also get a standard deviation, at least an empirical one, which they actually measure. In their
You
paper.
don't use generative methods for real science or medical.
For medical, yeah, maybe not, even though there are some works in that area.
You, as you said, you can use it as an intuition to what may be
Right.
a correct solution, but you can
Yeah.
never use it as a true solution because
Yeah.
there's always artifacts.
Let's say it shouldn't make a decision in a hospital right now. But yeah,
Hopefully.
hopefully. And there's also one more problem, one more paper which applied the DRM, which also has DRM in the paper title, to blind inverse problem where you don't exactly know the full extent of H. So maybe you know it's a blurring problem, but you don't know the actual hand movement while taking the image. So yeah, had a couple of nice follow-up papers. These are some more results from DRM. If you want to take a look at our code and the project webpage are available online through the QR code as well. And thank you very much for listening.
Any questions?
Yeah.
How fast it is in inference time or generation time actually in this
Oh.
case?
So at inference time or generation time or solving time, we use 20 steps as opposed to the thousands that we've heard. So you want in terms of seconds. So 20 steps on a traditional GPU, again another crazy GPU, takes around for a single image 5 seconds. So it's not that bad. It's at least 5 times as fast as previous techniques that solve similar tasks.
Thank you.
Thank you very much. Thank you all for coming.
תודה לבלה ושחר.
תודה לכולם.
תודה ממש.